Hello class, this is going to be our flipped classroom on orbital notations and electron configurations. As usual, feel free to pause this video at any point to take notes. Now I'm going to warn you ahead of time, this can be a little bit of a complex topic, so please bear with me, and if you still do not understand, remember to ask questions in class. So first of all, what exactly is an orbital notation? We already talked about how the electrons are located somewhere outside the atom, but we didn't specify where outside the atom. So first, let's note that electrons are found in specific levels or shells around the atom. And there are up to 7 levels of electrons. So if you were drawing a picture of an atom, it might look something like this, where the center is where the nucleus is, the protons and neutrons, and then you have levels and levels and levels around the atom up to 7. So I'm showing you level 1, level 2, level 3, and again it can go up to 7. And obviously, the further away the electron is, the further level it's on. The levels also have higher energy as you go further away from the nucleus. So level 3 has more energy than level 2, and level 2 has more energy than level 1. Next, within each level, there are things called sublevels. So each level has different sublevels, or if you want, these are shapes that are found within the shells. Level 1 has only one sublevel, and that is called sublevel 1s. Level 2 has 2 sublevels, that is 2s and 2p, and I'll explain this a little further a little bit later. Level 3 has 3 sublevels, the 3s, the 3p, and the 3D. Level 4 has 4 sublevels, 4S, 4P, 4D, and finally 4F. And then once you get past level 4, levels 5 through 7 have the exact same thing as level 4 does. They have an S, a P, a D, and an F sublevel. So next, I want to talk about something called orbitals. So we have electrons are found in levels or shells, and then within those levels there are sublevels or subshells, and then within the subshells there are something called orbitals or orientations. And I'm going to signify an orientation with just a simple line. So starting with the 1s sublevel, there's only one orientation or one orbital where you're going to find electrons. The 2s has also one orientation or one orbital. And the same is true for any other s, a 3s, a 4s, all the way up to 7s. They only have one orbital. The p's, however, have 3 orbitals. We can even call them 2px, 2py, and 2pz. And the same is true for any 3p, 4p, 5p, etc. They all have 3 orbitals. The d's have 5 orbitals. So 3d has 5 orbitals, 4d has 5 orbitals, etc. And then finally, the f's, the f sublevels, they have 7 orbitals. Last thing you need to know about the orbitals, each orbital can only have a maximum of 2 electrons, no more than 2. And these electrons, if they are in the same orbital, for example, if you have 2 of them in the 4s, they must spin in opposite directions. And the reason for that is that electrons are negative, so they would repel each other. So if they're in the same close area of space, they would push each other as far apart as possible away. So now I'm going to show you how this relates to the periodic table. To do that, you need to understand 2 things. Number 1, electrons must fill lower energy levels before going into higher levels. So if I tell you there's an atom that has 2 electrons, they have to start at the first level before they can go on to a higher level. Second, electrons must only have 1 in each orbital of the same sublevel before they pair up. So in other words, if I go back to this picture and I were to say to you there are electrons in the 2p, you'd have to put one in each orbital first before you were allowed to double them up. So I'm now going to go back and forth between the periodic table of elements and my notes here. So let's start with the first atom, hydrogen. Hydrogen has one proton, which means it also has one electron. So where is this one electron? Well, it's in the first ring of the atom. Let me go back to my very first page notes. It would be somewhere in this level, somewhere floating around here. And what do we call that area? That is the 1s. So to designate that, I've written 1s with an arrow. Now let's look at the second atom on the periodic table, helium. There it is. Notice that helium is still on the first period of the periodic table. The periods are actually the levels. This is level 1. So helium has 2 electrons. They are both on level 1. As a matter of fact, they are both in the 1s orbital, right there, that line. So you can see I've drawn 2 arrows. The arrows represent the electrons. Notice I drew one up and one down, because like I said, the electrons, if they're in the same orbital, they can't spin the same direction. They would bump into each other. So that fills up the first level. Helium has a first level that is complete. Let's move on to element number 3, lithium. Notice that lithium is on the second row of the periodic table. That means it's the second level. But that doesn't mean that all of its electrons are on the second level. It has 3 electrons. The first 2 electrons of lithium are just like helium's first 2 electrons. They're in the 1s. But once you've filled up the first level, where do you put electron number 3? In the second level, in the 2s. Then if we keep moving, beryllium has 4 electrons. Okay, no surprise here. Beryllium will have 2 electrons in the 1s, just like lithium, and it'll have 2 electrons in the 2s. A lot like lithium, but now it has another electron. Remember, it has 4. Now things get a little more confusing. By the time we get to element number 5, boron, you can see that boron is still on level 2. There's no question about that. But look where it is. It's not over here. It's on the other side of the table. This section of the periodic table is called the p section. Can you guess why? Because this is where the p electrons are found. These 2 rows here, this is called the s section. This is where the s electrons are found. So as I said, boron has 5 electrons. So how do I designate where those electrons are? Well, the first 2 are in the 1s, next 2 are in the 2s, and then the 5th one is in the 2p. Notice I put the first arrow there. As I keep going through the table, let's just do this all together. Carbon, nitrogen, oxygen, fluorine, and neon. You keep putting in another electron, another electron, another electron, so it looks like this. Here is carbon. It now has 2 electrons in the 2p in addition to everything else. Here is nitrogen, 3 electrons in the 2p. Then when we get to oxygen, where do we put the next electron? Well, we put it back in the 2p, but now we can double them up. Remember that rule I said you're not allowed to double up until you have 1 in each? Well, after nitrogen, we've had 1 in each. Now we can double them up. So then we get to fluorine, has another one. There's the new one for fluorine, that down arrow right there. And then when we get to neon, we've now filled up not only the 1s and the 2s, we filled up the 2p. As a matter of fact, we've actually filled up, for neon, the entire second level. There's the second level. We filled it all the way up to neon. The second level is done. I'm just going to do one more example. Where would we put electron number 11? Well, look where it is on the table. It's on the 3rd level, the 3rd period, which means sodium has the same configuration as neon all the way up to 2p, and then the last one, you guessed it, goes into the 3s. Now, this is called the orbital notation. It's a very complicated way of showing where all the electrons are using a lot of lines and arrows. There is a simpler way to designate the same thing, and that is called the electron configuration notation. It is almost identical to the orbital notation, except instead of using arrows and lines, we're just going to use little superscripts to represent where and how many electrons you have. Hydrogen has 1 electron in the 1s, remember, from this picture. So instead of doing 1s with an arrow, it's 1s1. Helium has 2 electrons in the 1s, so it's 1s2. Lithium has, take a look again, remember here was lithium. So how do we represent 2 arrows and 1 arrow? We do 1s2, 2s1. And then as I just go down the list, I get beryllium, 1s2, 2s2. And then remember what happened when we got to boron? We started filling in p electrons, 1s2, 2s2, 2p1. Then carbon, 1s2, 2s2, 2p2, etc. all the way down. Nitrogen, 2p3, oxygen, 2p4, fluorine, 2p5, neon, 2p6. And then remember sodium? Filled up all the 1s, all the 2s, all the 2p, and then we finally put 1 in the 3s. Now, you might think, well, this is really confusing. Is there an easier way to show a configuration without writing all these numbers? Yeah, there is a shortcut, and that's called the noble gas configuration. So let me read this to you. It says, since electrons must fill up lower levels before going into higher levels, remember we talked about that earlier, if they have to fill up before going into their higher orbitals, we can represent an electron configuration starting from the right end of the periodic table, where the s and p orbitals are filled, and then continue from there. All we have to do is mention which noble gas we are starting from. So what am I talking about? Well, let me give you an example. Let's say I wanted to show phosphorus's electron configuration. Phosphorus is right here on the periodic table. It has 15 electrons. Wow, that's a lot of electrons. That would be 1s2, 2s2, 2p6, and then 3s2, and then 3p3. I can shorten that by saying, look, if you're telling me I have electrons in the 3rd level, I already know the rule that you're not allowed to have even 1 electron here unless this entire 1st and 2nd level is filled, right? So why not just say, hey, instead of starting at the beginning, let's do this. Here is phosphorus on the periodic table. Let's not start all the way from electron number 1. Let's start from the end of the table right here, neon. Why neon? Well, because phosphorus is on the 3rd row, I have to assume that the first 2 rows are filled, right? That's a rule. So instead of saying 1s2, 2s2, 2p6, let's just replace that with the symbol for neon. So instead of phosphorus being 1s2, 2s2, 2p6, 3s2, 3p3, let's just say that phosphorus is neon, 3s2, 3p3. Because this is neon. This makes your life so much easier, especially if you had to do an element like, oh, I don't know, francium, 87 electrons? I don't want to write down all 87. This is what I would do. I'd say, oh, you want to know francium's configuration? Well, we'll start with radon, because we know radon is filled, right? It's all the way at the end, and then fill in 1 more electron for francium. And where would that electron be? Well, let's see if you can figure it out. What period is it on? 7? What section is this? The S section. So francium would just be radon and then 7s1. And now, one last thing to talk about in this video. There's also a term called valence electrons, and valence electrons just mean the electrons in the last shell or last level. So for phosphorus's example, we have all these electrons. The valence electrons would just be the ones in the 3rd level. It has 2 plus 3, 5 valence electrons. There's an easy way to figure out the number of valence electrons for any atom just by knowing what group it's in with this little cheat sheet. Anything in group 1 has 1 valence electron, anything in group 2 has 2 valence electron, and then 13 through 18 have 3 through 8 valence electrons. So just as a random thing, if I were to pick a random element, let's say bromine, Br, and I'd say, how many valence electrons does bromine have? I know it has 35 total, but how many electrons does it have in the last shell? Well, I could either count, or I could go, hey, wait a second, it's in group 17. That means it has 7 valence electrons. What about silicon? How many valence electrons does it have? Well, it's in group 14. it has 4 valence electrons. What about these guys? Everything in here, 1 valence, everything in here, 2 valence. And that is our flipped classroom on orbital notation and electron configuration.